So in this lecture, we will discuss mutual exclusion algorithms. So this will be our full-fledged lecture in which we look at distributed algorithms per se. So we will extend the basic lecture that we had discussed last time. So the key prerequisites would be logical clocks, right? So Lamport clocks, both scalar Lamport clocks as well as vector clocks. The next important prerequisite here would be Lamport's algorithm for mutual exclusion. Of course, assuming our asynchronous setup where we don't have clock synchrony. Alright, so in this lecture we will discuss two kinds of algorithms. One is without tokens. So we will discuss the Ricart-agarwala algorithm and the Mekava's algorithm. Then we will discuss token based algorithms as a part of this slide set, where we will discuss two algorithms again, the Suzuki-Kasami algorithm and the Raymond's tree algorithm. So coming to the Ricart-agarwala algorithm, so again the key prereq is to understand the Lamport's algorithm that was a part of the previous lecture. So in that algorithm we said that we would require 3 times n-1 messages for achieving mutual exclusion, and we had proved that it is correct. So now I'm just extending from there, and of course the prereq is that that algorithm is completely understood. So that algorithm had 3 rounds. So where we send a request, then we send an ACK, and then we send a release. So the question is that is a timestamped reply or an acknowledgement necessary, right? So that's the key question. And so the main idea is that instead of these 3 messages that I send to every single node, can I make 3 to 2? Then instead of 3 times n-1 messages, I will have to send 2 times n-1 messages, which is an improvement. So the idea was that in the Lamport's algorithm we send an acknowledgement immediately, because we have to show that another node has recorded the message and it is sending an acknowledgement with a greater timestamp. So the key insight over here is that we hold on to the acknowledgement and we piggyback the acknowledgement along with a release message. We'll see how. So this will help us reduce the number of messages from 3n to 2n. So here is the algorithm. Process I sends a timestamped request message to all other nodes. Alright, so we had seen this. So this part is the same to all the other nodes. So the rest of the other nodes, it sends a timestamped request message. When process J receives a request, it sends a reply if. So this part changes. The first is PJ is neither holding the lock nor is it interested in acquiring it. Alright. So if it is not interested at that point of time in acquiring it, or if it is not holding it, it just sends a reply. And the reply would follow the same rule for scalar Lamport clock. So its timestamp would be higher than the request. Or second condition, PI's request timestamp is smaller than PJ's request timestamp and PJ is not holding the lock. So this basically means that PI made an earlier request. So even though PJ is desirous of acquiring the lock, so lock means the shared resource. I'll often use lock in place of shared resource. So this kindly understand, because in the concurrent systems world, any shared resource is actually called a lock. So coming back to our discussion, the thing is that look, if PJ is not holding the lock or not interested, it will send a reply. Or if it is interested, it has sent out a request, but PI's request happens to be smaller, the way we defined it in the previous lecture, than PJ's request, then also it will send a timestamped reply. Alright, so this part changes and this part is crucial, right? So the key idea is that PJ will send a reply only if both of these conditions hold. So now when do you acquire a lock? Well, you acquire the lock when a process has received n-1 replies. So let me just go back. So what would happen is that PJ will not send a reply as long as these conditions hold. So let me put it in a different way. It is not that PJ is going to junk the request from PI. Process J is not going to do that. What process J will do, PJ will do, is that it will hang on to PI's request until one of these conditions is true. Subsequently, it will send a reply. And once a process PI has received the n-1 replies, it knows it can acquire the lock, so it will acquire the lock and finish its job. And after, so releasing the lock basically would mean doing the same, which means replying to all the pending requests, which the requests it has kept pending, it has not replied to, it will reply to them, right? After it releases the lock, it will reply to all the pending requests. So one thing that is obvious over here is that instead of sending 3 messages to every node, we are sending 2, right? So the release is not there. The ACK and the release we are fusing into one message. So instead of sending 3, we are sending 2. So the key idea over here is that I send a request, other nodes simply hang on to my request, keep it pending until one of these conditions holds true. Once they hold true, it holds true, they send a reply and they get rid of my request. So then cleaning up the state is not an issue. And once I get all my replies, I enter. And subsequently, if process I, which is me, if I have kept other requests pending, I will reply to them. So this is a simple algorithm. What about the proof? So hopefully the algorithm and understanding its 2n-1 has not been an issue. But again, I would like to say that the Lamport's algorithm is a prerequisite. Kindly not go through this unless you have understood that thoroughly. So again, let us prove by contradictions. Assume that processes Pi and Pj both have acquired the lock at the same time. With no loss of generality, same approach, assume Pi has a lower request timestamp. This means that Pi must have gotten Pj's request after its request. That is obvious, right? Why? Because the thing is that if let's say Pi's timestamp is Ti, then it could not have gotten Pj's request because otherwise Ti would have had a higher timestamp and this relationship would not have held. Given the fact that this relationship is holding, it means that Pi must have sent its request, must have gotten Pj's request after it sent its own. Alright. So then this means, according to this algorithm, the moment process I got the request from process J, it had already sent out its request. Furthermore, its request timestamp was less than the timestamp of request J, correct? Consequently, it is not possible via this condition, right? First, it was interested in acquiring the lock, and second, of course, this condition doesn't hold, but for this condition, when it was interested, the request timestamp of Pj was higher than its request timestamp, hence it couldn't have sent a reply. Given the fact that Pi could not have sent a reply to Pj would have definitely not gotten a reply from I because I was the one with the earlier request and the one with the lower timestamp. Consequently, Pi didn't send a reply to Pj, so clearly Pj's conditions that it would have gotten a reply from everybody would not have held. Hence, Pj could not have acquired the lock. Given that Pj could not have acquired the lock, we have a straightforward contradiction over here. So I am not explaining this proof once again, because this proof, if you think about it, is extremely simple. But I would request the viewers to keep replaying this part of the video where I explain the proof until they understand it thoroughly. Let me explain it in another way. The key idea over here is that unlike the Lamport's algorithm where we send a reply immediately, here we hang on to the reply. So the argument that is being made, the same argument was made over there also, that there is no way that I would have received, right, process I would have received process J's request before it sent its request. Otherwise, by the law of scalar clocks, it would have had a higher timestamp. That is not the case, which means it receives after it. And if it receives after it, it already has its own request in its queue, which has a lower timestamp, so a reply could not have been sent. If a reply could not have been sent, there is no way that PJ could have acquired the lock. I was about to say enter the critical section, but again that is also not wrong, because that's also another way that we refer to mutually exclusive objects in concurrent systems, but I would prefer not using that. So, but the key idea is PJ could not have concurrently entered the critical section or acquired the lock. Same thing. Alright. So there is a contradiction here, which means proof by contradiction, the algorithm is correct. And as opposed to 3 times n minus 1, alright, we have an approach which is 2 times n minus 1. So clearly there is a 50% benefit. And the key insight is that defer the reply. That's the key insight. So every algorithm, has to give us an insight, right? So the key insight over here is that we simply defer the reply. So this deferral is reducing 3 to 2. Alright, now we will try to reduce this order n business to order square root of n. So we will discuss the Mekava's algorithm. So the main reason for a linear number of messages is basically we send a message to all the sites and we also expect replies from them. So the key insight is, let's not send a message to all sites, let's send a message to a subset of the sites. So let a set of processes associated with a process be called as request set Ri, which is a subset. For any two processes, let us guarantee that for two processes Pi and Pj, we have Ri intersection Rj is not equal to 0, it's non-null, which basically means that if process I has an intersection set, if process J has a request set, then the intersection regardless of I and J is always non-null, or which means there is one process which lies in the intersection of both the request sets. So we are not considering faults here. So let us take faults out of the picture. So it appears, it happens to be the case that it is possible to construct such request sets where we can say that the size of each request set is square root of n values, or what I can say is that for every I can have a request set such that consider any other j, process j, its request set, there will at least be one process in common, right? So the intersection will be non-null and the size of these will be in the ballpark of square root of n. So of course this will require results from field theory, so we will not go that far. We will consider a simpler argument. So consider n cross n processes and consider process I. So process I can give it a coordinate in the 2D space, right? Right, so or let's put it this way, consider n processes and let's consider n processes, let us arrange them in a root n cross root n matrix. And let this be the position of I. So I can say that all the processes in its row and in its column comprise its request set. Alright, so what did I do? I took all the processes, n processes, arranged them in a root n cross root n matrix. So every process has a coordinate in this matrix. And I say that for process I, I'll consider all the processes in its row and in its column to be a part of its request set. And this automatically guarantees to me that regardless of the j, the value of j that you choose, For example, it can be this one. As you can see, this will be the request set of j, and the intersection is non-null. So of course the size of the request set over here is 2 times square root of n, but that's okay, we will live with this. It's still order root n, so we will live with this. And let's, using this assumption, let's go forward. But of course the only assumption we will need is that the intersection is non-null, and bear in mind that this is a simple way of constructing such kind of non-null intersecting request sets. But if you want to go to square root of n, you'll have to use field theory, and that's also not that hard. So here is the algorithm. So this algorithm is slightly involved, but not all that involved. So what happens is that pi, so the first part is the same. So the first phase is the same, where process I sends a timestamped request message to every node in Ri, including itself. Right? So previously what was happening? That you are sending a request message to every other node in the system. This is not happening now. A message is being sent to every node only in the request set, which includes itself. Upon receiving a request message, a node pj, which is a part of Ri, marks itself as locked if it is not already locked, and it returns a locked reply to pi. So you can see this part is pretty similar to the Ricart-agarwala construction. So it is not all that different at all. So up till now it appears that we are proceeding along the same line, where if a node pj, process pj, in the request set, if it is not already locked, then it says, look, I have no issues in being locked for process I, so let me mark myself as locked. So it will return a locked reply, right? It will mark itself as locked, and it will return a locked reply to pi. In the sense, it is committing to pi that I stand behind you, and if you want to acquire the lock, go ahead and acquire it, and essentially I have reserved myself for you. So this is similar to the Ricart-agarwala construction, even though this notion of reservation was not there, but nevertheless the key idea is that if the node pj, if it is unlocked, it will mark itself as locked and send a locked message back. So in the trivial case where there are no other competitors, the entire request set will send a locked message back, and then process I will be sure that everybody in its request set, all of them were free, and then there are no objections with me acquiring the lock, so process I can simply go forward. Now let's look at the next part. This part is slightly interesting. If pj is already locked by a request from another process pk, here is what we need to do. pj will then place the request from pi, which is me, in a wait queue. Alright, so it uses the same basic notion of deferral that we used in the Ricart-agarwala construction, that if pj is already committed to some other process pk, it will place pi's request in a wait queue. If the locking request or any other request in the queue precedes the current request, then send a failed message. If the locking request, in this case the locking request is from pk, alright. So if this request or any other request in the queue precedes the current request, in the sense it has a lower timestamp, then we send a failed message to pi. So in this case what happens is that pj basically tells pi that, look, I have other messages in my queue which have a lower timestamp than you, so hence I'm sorry, I cannot lock, and I'm sending a failed message. Otherwise, if that is not the case, which basically means that if pi is coming with the least timestamp, so then the message from pi should get a higher priority. As a result, an inquire message is sent to pk to find out what is happening. Alright, so what is the key idea? The key idea is that from the point of view of pj, which is getting a request from pi, right? If it is unlocked, no problem, it will send a locked message, right? If let's say it is locked, then it will see what is the priority of the request from PI vis-a-vis the other messages it has. If it has a lower timestamp, okay, then it clearly means that it's a high priority message, so it sends an inquire message to PK which has locked it to ask what has happened. If that is not the case, then it sends a failed message to PI basically telling it that look, I was not able to lock. Alright. So these messages are clear. So the idea basically is that the contention is at PJ, which is already committed. If I am a high priority requester, in the sense my priority is low, my timestamp is low. Sorry, high priority means timestamp is low. Then what I do is I request PJ to inquire with PK. This is always the case, right? I am in an office, somebody important comes. Then I just gauge the person's importance with respect to what I'm currently doing. So let's say I'm talking to somebody else on the phone, and let's say somebody comes who's extremely important, then I place the phone down and I talk to the person. But vice versa, if I'm talking to somebody very important and let's say somebody less important comes to my room, then I just continue talking and send a failed message. So this is very similar to that, it mimics human behavior in this part. So when PK receives an inquire message, it basically means that somebody is knocking on its door that look, somebody more important than you has arrived, what happened? If PK has received a failed message and knows that it cannot succeed, then it will send a relinquish message. Fair enough. So if PK knows that it does not have a chance of acquiring the lock because it has already been spurned in that sense, it will send a relinquish message. Otherwise, it will simply defer the reply and it will not do anything. So who are the actors in this game? The actors in this game are PI, PJ and PK. So think of this as, let's say PJ is me and I'm talking to PK on the phone, and then PI arrives. So if PI sends a request message, so of course the trivial case is that there is no PK in the picture. In this case, I just send a locked message to PI and I'm done. But I'm not looking at that. I'm looking at the more interesting case where I'm talking to PK, in the sense I'm already committed to PK and PI arrives. So if it is the case that either PK has a lower timestamp than PI, or I have other requests in my request queue who have a lower timestamp than PI, I simply tell PI that look, you have no chance, you're too unimportant for me, so you in a sense go away. So I send a failed message. If that is not the case and PI happens to be somebody very important, like for example if I'm talking to a student on phone and the head of the department arrives outside my door, well then what I tell is I send the student an inquiry message and I tell the student, do you mind if I put the phone down? So then the student basically sees if there is any chance of continuing the conversation. So in this case, PK basically sees if it has received a failed message or not from others. If it knows anyway it doesn't have a chance, he doesn't have a chance in acquiring the resource. In this case, it means that doesn't have a chance in getting whatever he or she wanted. Then of course it makes sense to send a relinquish message to say that look, you go and lock yourself for somebody else, I don't care. Otherwise what will happen is that PK will simply defer the reply and reply later. Alright, this sounds to be a lot of fun with PI, PJ and PK. Now what else happens? So now when PJ receives the relinquish message, it realizes that PK does not have a chance of acquiring the lock. Right? So what needs to be done? So it locks itself for the earliest message from PI dash in its wait queue. So what it does is it takes a look at its wait queue. So in the wait queue there are a bunch of requests including the one from PI. It locks itself for the earliest message from process PI dash, which could be PI. So it locks itself, it changes its status. So it basically means if the student tells me on phone that the student is okay with me hanging up, I just hang up and talk to my head of the department. Furthermore, what it does is that it sends a locked message to PI dash telling it that, look, I have locked myself for you. And it adds the request from PK, the one it just ditched, into its wait queue. So essentially the idea is that if there's somebody important at your door, you ask the person whom you are talking to on phone to kindly hang up. And of course you are polite in the sense you wait for a reply from that side. Right? So in this case, this is what is meant by PK deferring the reply. Alright, so this sounds simple enough. So when does the process acquire the lock? It acquires a lock when it has received lock messages from its entire request set. Right? So when from the entire request set, it gets locked messages, it acquires it. And why is this algorithm correct? Well, the algorithm is of course correct. The reason being that one process can never lock itself for two other processes, right? So basically, given that two request sets will always have at least one intersecting process, and that intersecting process cannot commit to both, so it is not possible for two processes to acquire the lock and essentially break mutual exclusion. Mutual exclusion is essentially a long form for mutex. So it is not possible for this to happen. Releasing the lock. Well, once a process is done, it sends release messages to all the processes in its request set. A process in the request set locks itself for the earliest request in the wait queue and it sends a locked message. It sends it a locked message. If there is no such request, it marks its status as unlocked. So this part is easy. And this has been a common feature in, so this was there in the Lamport's algorithm as well. Proof. So the proof for mutual exclusion is easy. It is basically assume two processes PI and PJ have the lock simultaneously, which means there has to be a node PK that must have given lock messages to both at the same time. That is not possible. So as we have seen, if let's say I am giving a lock message to PI, I will have to withdraw the locked message from somebody else. This is not possible. Given the fact that this is not possible, mutual exclusion is always guaranteed, but there are two more important things. What we need to look at is we need to look at deadlock and starvation. In the sense, is it the case that process A is waiting for process B, right? Process B is waiting for process C. Process C is again waiting for process A. So do you have a circular wait? If you have a circular wait, so why are deadlocks important? Because in any algorithm where we wait, the chances of a circular wait are always there. That was not there in the Lamport's algorithm because we never waited. But in algorithms where we actually wait, the chances of a circular wait are definitely there. And so this is, we need to look at deadlocks, and the other is the issue of starvation, which means that is it possible that there is one message but it starves, in the sense it never gets the lock. Right? So we'll look at them. We are saying it is not possible, but we'll look at them in some detail. Alright, so this finishes the algorithm. So we will now go for a deeper discussion of Mekava. It finishes the slide part. So now we will go for a slightly deeper discussion using our e-notebook. Alright. So what again was the idea? We had three actors, PI, PJ and PK. What was PI doing? It was sending a request. If PJ was unlocked, it was sending an immediate commitment that okay, I'm locked for you. But that's not clear. That's clearly not the simple case. And then, we are not looking at this because let's consider the more difficult case where our good friend PJ has already committed to PK. So then in all cases within its request queue, it always puts in PI's request, right? So requests are not sent once again. Requests are sent only once. Okay, they are clearly not sent once again. So even though the request is there in here, it sees the priority of this request with respect to all the requests that it has. If it finds that this request is the lowest timestamp, it is the time to tell PK that look, I have received a request with a lower timestamp from PI. And so basically you kindly tell me what you are up to. And let's see if this is not the case, in the sense there are other requests, including the request from PK, that have a lower timestamp or a higher priority. Then of course a failed message is sent and the PI is told that, look, I can't do it immediately, right? So there is clearly no waiting over here, in the sense that the failed message is sent immediately, but the inquire message is also sent immediately. But as far as PI is concerned, it is not going to get a reply from PJ immediately, right? It can get locked and failed immediately, but not others. We will see why. So when it asks PK to respond, if PK is holding the lock, of course it will not respond. But let's say that PK has also requested a couple of people in its request set. Nobody has sent a failed message. It will just defer the reply. It will simply defer. And let's say if somebody says that, look, I can't satisfy your request, then of course what comes back is a relinquish. So then PK also records the fact that PJ is not locked for it. Then PJ is now ready to lock itself for any other message. So it takes a look at all the messages in its request queue, which now include the request from PI and PK as well. So let's say the one with the lowest timestamp is PI at this point. So then it sends it a locked message and it locks itself for it. Or let's say it sends a locked message to somebody else, and ultimately PI's request will become the one with the lowest timestamp, right, at some point. So what we will discuss now is, this is the basic idea. So some key points: a request message is never sent twice. A request message is never sent twice. Right, so that is important. So once I send a request message to everybody in my request set, it remains in their queues. Okay, so even if they tell me failed, that means that I can PI, if I am PI, I can go and lock myself for somebody else. But essentially that's it, right? But a request message is never sent multiple times. That is point number one. After that, if you think about it, everything, so a message remains in the queue. So a message remains in the queue until a release. So until you don't release it, it remains in the queue, right? So it will continue to remain in the queue. There is no issues. What will happen is that mutual exclusion guaranteeing is not a big deal at all, because the reason is that any node at one point of time, so node means a process here, is locking itself only for one other process. See, it will never be the case that actually two processes have acquired the lock at the same time, because in their request sets, one intersection will be there and that guy would have only committed to one, not the other. So that's the reason one of those processes would not have gotten a locked message from everybody in its request set. So mutual exclusion is guaranteed. But what we should look at are two things. One is deadlocks. So deadlock, as I said, is a circular wait. And why? Because we are waiting over here. If PK has not gotten any failed message, we are essentially waiting. So since PK is waiting, PJ is waiting. Since PJ is waiting, PI is waiting. Correct? So we have a wait over here, PI, PJ and PK. The other is starvation. Starvation means that I have a request, but the request is simply never getting the lock, right? I might not have a deadlock, there is no cyclic wait, but I am simply never getting the lock. So there is an interesting result that is there, which is that starvation freedom, if I can show that I never starve. In a sense, if I am there in the system, I'll ultimately get the lock. Starvation freedom implies deadlock freedom. It's very important. Deadlock freedom doesn't imply starvation freedom, but starvation freedom implies deadlock freedom. So let us look at proving this. So if we can prove it is starvation free, of course it is much easier, but we will take a slightly different route. So let's understand what exactly is happening. So we have Pi, we have Pj in this case, and we have Pk. So Pj, as far as we are concerned, is incidental. So pretty much Pi is waiting on Pk. So it basically wants Pk to relinquish such that Pj can give Pi the locked message. Alright? So what is the relationship between the priority, or let's say the timestamp of I and k? Well, clearly Pi is waiting on Pk, the primary reason being that Pi has higher priority or it has a lower timestamp. So pretty much this holds. See, if Pk is waiting on some other process, doesn't matter what it is. So again, this will also hold. Alright. And similarly, if that is waiting on some other process, again this relationship will hold. So it is clear that because of this less than ordering, a cyclic wait is not possible. Right? So this is clearly an ordering which is not symmetric, in the sense that it is not possible to have some other Tz and again some other process Z and that waiting on I. That is not possible, because as you can see, this relationship, the less than relationship, needs to hold. So a cyclic wait is not possible. So given that a cyclic wait is not possible, a deadlock is not possible. Alright. So this basically means that when we have proven deadlock freedom, it automatically means that in the system, you will not have a situation where nobody is making progress and nobody is acquiring the lock. That will not happen. Somebody will. Alright. So that is very important, that somebody will definitely acquire the lock. So now let's prove starvation freedom. So as we have said, starvation freedom implies deadlock freedom, not the other way. So we didn't find a good way of proving this protocol to be starvation free, but at least we have proven it to be deadlock free. So for starvation freedom, we don't have to do much. This is actually easier. Given that we have proven deadlock freedom, we can use some of it to prove starvation freedom as well. So the key idea of starvation freedom is like this. Okay? That consider the process with, let's say, the least timestamp in the system. Let it be Pi. And let this be its request set Ri. The moment it has sent a request to everybody, alright, Pi's request is present in the request set of everybody. Right? Subsequently, any other message that they send has to be more than the timestamp of Pi. But in any case, we are assuming that among all the requests, Ti is the minimum. It has the least timestamp, or in other words, it has the greatest priority, right? So this is what we are assuming. Second, we are assuming that other requests are getting served because it is deadlock free. So at any point of time, some or other request will get served. Now the question is, when will the time for this request come? So once the request message has been sent, it has been enqueued in all the queues. And we are sure, given the Lamport clock property, given the fact that we have this max operation, the timestamp always increases. It never reduces. So we will never have a situation in the future where a request will be sent with a lower timestamp. That's not going to happen. Why? Well, because we have sent messages everywhere. Every message that is being sent in the entire system, this is the smallest timestamp. So clearly, in the future, no message will be sent with a timestamp less than this. Given that that has happened, let us just consider all the nodes in the request set, and that includes PI itself. So they will basically never send a lock, they will not send a locked message to any other request after getting the request from PI, right? So that is clear. So that follows from our property, and that is mainly because this is the lowest in the system. So subsequently, if anybody else tries to send a locked message to this, all that it is going to get is it is going to get a failed message back. So it is not possible. So after a certain time, of course, let's say all the messages which are there in the system may clear up. But ultimately what will happen is that all the nodes in the request set, Ri, will simply not participate in any other locking protocol, right? And they will basically ask all the members of their request set to kindly send relinquish messages, and they will not participate in any new locking protocol, right? So when they get it, first if they have locked themselves for somebody else, they will immediately send an inquire message asking it to release the lock. And subsequently, they will not entertain any newer message. They will keep on sending failed messages. And because it is deadlock free, gradually the messages are draining out from the system. So ultimately, it will be the case that this request, the request from process I, is pretty much at the head of every queue, and all of them have sent a locked message back, because they are not sending a message to anybody else, right? And the system has to make progress. It is deadlock free. No other request is able to make progress. A time will come because all of their timestamps are greater than Ti, right? And furthermore, so consequently, they have a lower priority, and they will not be able to make progress, and they will also not be able to lock the nodes in the request set, because the request set will not accept any requests. And then the request set, the nodes of the request set will continue to send locked messages to PI, and ultimately it will get all the locked messages and will start to execute. So this means that this protocol is starvation free, because it is never possible that one request will wait for eternity to actually get the lock. Why? Because ultimately it will become the request with the least timestamp, and all the nodes in its request set will either inquire and ask for relinquish messages and stop any subsequent messages by sending, stop any subsequent requests from sending by sending failed messages. So the victory is for this process. So this is why starvation freedom is avoided. And so this completes the proof that this protocol is both deadlock free as well as starvation free. Let us now compute the number of messages that are sent. So for a single request, we need to send square root of n minus 1 request messages. That is to every node in the request set. We need to send square root of n minus 1. So we will receive square root of n minus 1 locked messages. If let's say our luck is really bad, we might also receive these many failed messages. Furthermore, if let's say the priority of the requester is very high, then a maximum of, again, these many, alright, inquire messages will be sent. The reason is that let's say at every PJ in its request set, if it has the highest priority and that is locked by some other process, then an inquire message will be sent. And it is possible that a maximum of these many relinquish messages will come back. So we can say that the maximum number of messages is 5 times square root of n minus 1, which is conveniently put as order of square root of n. So what we have done is we have done significantly better. From 3n minus 1 we came down to 2n minus 1 to order of square root of n. So the Lamport's algorithm was this much. Then the Ricart-agarwala algorithm was this. And then we have the Mekava algorithm, which is order of square root of n. We'll discuss the two token-based algorithms, the Suzuki-Kasami algorithm and the Raymond's tree algorithm. So they differ in terms of their philosophy as compared to the previous algorithms. So the idea over here is that a site can access the critical section, a process can access the critical section if it has a token. So every process maintains a sequence number or a request ID. So a request is of the form, it's a tuple of I comma m. So I means that I refers to process pi, it's the process ID I. And m is the sequence, it says that it needs the mth access to the lock. Alright. So this does take some amount of past history into account, but not much. Essentially every request in this case is a tuple of the process ID and the access number of the lock, in the sense is it your third access or fourth access or fifth access to the lock. Furthermore, every process pi keeps an array of a sequence array 1 to n, where the jth entry is the largest sequence number it has received from j. So think of this as some sort of a vector clock. So the idea is similar to a vector clock. We were using scalar clocks earlier. So this has been inspired from the vector clock. So when pi receives a message j comma m from process j, what it basically does is akin to what we do in a vector clock. It sets the jth entry as the maximum of what it had and the value that process j is sending. Alright, so what is the idea? The idea is that you have a scalar clock, which is the sequence, which is m in this case, and you have a vector clock, a sequence array. So alright, so this is the state that a process keeps. What is a token? It's a queue of requesting sites. Sites is the same as process over here. So it's a queue and it's an array of sequence numbers. So we'll see what they do, array C. So Ci is the sequence number of the latest request that pi executed. Alright. So basically it is saying that, let's say if Ci is 3, this means that pi process I just finished the third access to its lock. Just finished means finished in the past, the third access to its lock. So this is the array Ci. So we have many data structures here. So I would request you to kindly go through this piece of the video many times to memorize what these are. So for a process, we have its internal variable m, which is essentially its lock count. It's a scalar clock. Sec is a vector clock, right? And then for the token, we have two fields. One is the queue of requesting processes and other is an array of sequence numbers C, capital C, where Ci is the sequence number of the latest request that the ith process executed, ith process finished. Alright, so there are these four things for a token, Q and C, and for a process, M and Sec. So let's not forget these. Okay, M and Sec for a process, Q and C for a token, not to be forgotten. Great. So to request the lock, what you do is that, so this is very similar to a vector clock. It increments its ith entry, so it pretty much increments m. So in the vector clock, it says that, look, I'm going to request, so it increments that entry. And the current value it puts a temporary variable val, and this I comma val is sent to all the sites. So it is basically saying that look, I am process I just incremented my internal scalar count, now it is val, and I need access to the lock. When pj receives I val, what does it do? Well, it does the standard thing that it increments its vector clock. So it sets the ith entry as a max of sec j I and val. If the token is idle, in the sense, if the token is idle, meaning that we will see what it means, but let's say it's not being used and it's there with pj, then it sends the token to pi. If, right, if, so this if is important. If sec ji, which means as far as the token is concerned, as far as process j is concerned, the value of I that it is getting, which was essentially set by this operation, is equal to ci plus 1, which basically means that look, the token is recording that process I has finished 3 requests and now the 4th request is coming. 4 is equal to 3 plus 1, which means it's the next request, which means the token should be sent. Right? So it means it's not a stale message, it's not one of the old messages floating around, and this is genuinely a fresh request, because this process has already accessed the log 3 times. It wants to access for the 4th time, so access may be given. So if the token goes to a process, then it enters the critical section, which means it grabs the lock. So in this case, establishing mutual exclusion is rather trivial, because if you have the token, then you enter the lock and grab the resource, otherwise you don't. And given the fact that only one process has the token at any point of time, mutual exclusion is trivial. So we basically have to look for starvation freedom and deadlock freedom. And I want to repeat that we were able to prove in the previous lecture that starvation freedom implies deadlock freedom. Releasing the lock. Again, very easy. Pi releases the lock as follows. So it sets the ID Ci as the ith entry, which means that if, let's say, it finished the 4th access to the lock, within the C array of the token, it is going to add 4. As simple as that. Furthermore, for all j, it adds process j to q, which is the array within the token, which is the q within the token, as long as if sec ij, which means that in i's vector clock, it will look at the jth entry, if this is equal to cj plus 1, which means that it is aware of the fact that in some other process j has already acquired the lock cj times, but it is desirous of accessing it once more. So what it does, and let's say it gets to know that, because messages are being sent around, so j maybe sent some message to k and then k sent it to I, so that's all right. So it essentially scans its sequence array whenever it sees this relationship to hold, which means that process j is desirous of acquiring the lock for one more time. It adds it to the array q, the QQ. Then what it does is it dequeues PK from Q, and so it dequeues one process from the queue and it sends the token to PK. Alright. So for starvation freedom, pretty much if this is a first in first out queue, so it is guaranteed that as long as the process enters the queue, it will be dequeued and the token will go to it and it will access the resource. Alright. So what is the message overhead? Well, the message overhead is that look, if I have the token, I am the process, I have the token, I immediately grab it. Otherwise, it can be n. So n basically means that pretty much I send a message to n-1 other processes. Alright. And then ultimately one of the processes sends a token back to me. So it's n-1 plus 1. As simple as that. So why do I say that the requesting process gets the lock in finite time? because the request will reach all the processes in finite time. So by induction, one of these processes will have the token in finite time, because if I don't get it, if I assume that in an n-1 node system, one of them gets in finite time, if that is the assumption that I make, one of them will get it. That process would have seen my request. So my request will get added to the queue by precisely which line? By precisely this line, which means that if I have sent a request, alright, if I have sent a request and if the request either reaches directly or indirectly, it doesn't matter. But as long as it reaches any node which currently has the token, it is bound to add me to the queue. And sooner or later my time will come, and at max n processes will be there before me, n-1 rather. And so basically, and each one of them would have sent a message. So n-1 messages / processes, that's the way that you interpret this line. And there will be n-1 messages / processes before it. They will finish and my time will come. So clearly I cannot starve, right? So there is a built-in mechanism where I can't starve, because the moment that a process sends a request, it gets added to the queue. And furthermore, a process can also not swamp the network by sending multiple messages, because of precisely this little check that is done over here. So this little check basically says that, let's say that you have acquired the lock 3 times, and then in the next message you send 4, then only 1 will be added. If you send 1 more and then let's say that it becomes 5, then you lose your chance. In a sense, you get disqualified, right? So you can only have 1 outstanding request at any point of time. This also stops starvation to a large extent in this algorithm. So in this algorithm, proving starvation freedom was very trivial. So that's the reason I am not discussing this any further, because this kind of extends what we did in the previous 2 algorithms, Ricart-agarwala and Mekava. And starvation freedom is not there primarily because any process will basically send messages to the rest of the processes, right? The token has to be there with somebody, right? So the token, it's not possible that the token cannot be there with anybody, right? Otherwise the token is with this process, then there is no problem at all. If the token is there with somebody, it will see this request, it will add this process to the queue, and be rest assured, after a maximum of n-1 processes finish their request, the originating process will get the token. Now let us discuss one more approach, Rayman's tree algorithm. So here the idea is that nodes are arranged as a tree. Every node has a parent pointer. Furthermore, each node has a FIFO queue of requests. There is one token with the root, and the owner of the token can enter the critical section, which means grab the lock. So in the previous case, we said that the message complexity is either 0 or n. So let's say worst case is order n. So this is reducing order n to order log n for trees with reasonably high fan out. That is fine. But if we take a look at this tree, what we can see is a very simple arrangement. So let's assume it's a nice and balanced tree. Furthermore, every node has a parent pointer, a FIFO queue at each node. So let's see how this works. So the way this works is that as the token moves across the nodes, the parent pointer changes. So let's say the token moves from here to here. What you actually see is that, so just look at the previous thing. All the nodes were essentially pointing towards the root, and the root contained the token. In this case, the root has moved because the token will always be there with the root. So pretty much this arrow over here got reversed. Previously it was pointing in this way, but it got reversed. Now as you can see, still all the nodes point towards the token holder. And wherever the token goes, let's say next time the token goes over here, so as you can see, this arrow also got reversed. So pretty much all the nodes can approach the node that contains the token. of course the arrows do get reversed as the token moves. So they always point towards the token holder. So it is always possible to reach the token by following your parent pointers. So always your parent pointers will take you towards the token. That's the most important learning over here. Requesting for a token. So what it does is that within its own request queue, the node adds itself. So let's say that, you have an arrangement like this. So what a node would do is, within its own FIFO queue, it will add itself if it is requesting for the token. It will also forward the request to its parent. The parent will add the request of the child to its request queue. Furthermore, if the parent does not hold the token and it has not sent any request to get the token on behalf of any other child or itself, it sends a request to its parent and so on. So this process continues till we reach the token holder, which is the root. So the idea is very simple. I want to get the token. I insert a request into my FIFO queue. Alright, so far so good. Subsequently, what do I do? Subsequently, what I do is I send a request to my parent. Okay. And then my parent basically sees whether it has sent any request on behalf of any other child of its or not. If not, then it sends a request to its parent. Its parent again inserts the request in its own FIFO queue. Again sends a request to its parent. It does the same. Ultimately, we reach the token holder, which is the root. The token holder will wait till it is done with the critical section. Till it is done with the lock, it will wait. Subsequently, the token holder will take a look at the queue of the root node, which is the node that holds the token. Then the head of the queue, whatever node it is, it will remove the entry and it will update its parent pointer. Right? So basically what it will do is that it will remove the entry, send the token to that entry and update its parent pointer. So any subsequent node will do the following. Okay. It will dequeue the head of the queue. If self was at the head of its request queue, then it will enter the critical section. Otherwise, it will forward it to the dequeued entry. So let's give an example. So let's say that, this is the way that we had. And let's say this was the original requester node. And let's number these nodes 1, 2, 3 and 4. So then what happened is that this node added itself 1 to it. And it sent a request to its parent. So the parent, let's say, was not interested. So it also added node number 1 to it. And it sent a request to its parent. And let's say this was a token holder. So it added node number 3 to it. Because as far as it is concerned, node number 3 is requesting. Then once the token was released, what it did is that it said, okay, 3 is at the head of my queue. So then it reversed the direction of this arrow and it made 3 the token holder. 3 did the same thing. It said, okay, alright, so 1 is at the head of my queue. So let me make 1 the token holder. So it reversed the direction of its pointer. 1 becomes the token holder. And 1 sees that it is a token holder as well as 1 is at the head of its queue, so it uses the value. Right? If self was at the head of the request queue, then it will enter the critical section. Otherwise, it will forward it to the dequeued entry. So after forwarding the entry, a process needs to make a fresh request for the token if it has outstanding entries in its request queue. So mutual exclusion is very simple in any token based algorithm because the idea is that no two nodes can have a token at the same time. Deadlock. Circular wait cannot occur because all the nodes wait on the node that holds the token. And furthermore, we are not losing messages and we'll always have a rooted tree. And given the fact that we have a rooted tree, what will happen is as follows. Let me go to our paper over here. So pretty much what is happening is, if let's say this node is a requester, it is waiting on this node, and then this node is waiting on this node, but it is clearly not possible. So always, as you can see, these waits, right, are going along these parent edges, right? So a child always waits for its parent, but a parent never waits for its child. So let's say that the child always waits for its parent. Okay, so this is always happening, that let's say if I don't have the node, I'm asking my parent for it. If that doesn't have the token, if I don't have the token, I ask my parent. If my parent doesn't have the token, it asks its parent, so on and so forth. But the point is, you will never ask a child. As a result, given the fact that the tree itself is acyclic, you will never have a cycle of dependencies, because you'll never have a cycle of parent pointers, because you'll not have a circular wait. No circular wait implies deadlock freedom. So this approach will not have a deadlock. So now what was left? Starvation. So ultimately a starved process, this request, will come to the front of all the request queues. At this point it will have the highest priority, and the token will have to flow back to the starved process. So let us take a look at this once again. So let's say that there is one process, let's say this one. So what will happen is that this process, so let's call it process X, it will insert X in its own queue, send a request to its parent, X will be over here, X will be over here. And let's say later on, even if the parent pointers change, and let's say that the parent pointers go this way, that is all right. You will still have X over here, you'll still have X over here. So then what will happen is, the moment that the request is satisfied, right? So basically, mind you, we are always adding X as long as there is no other outstanding request that has gone from this node to its parent. All right. So then ultimately, when it will become the oldest, everybody will find X to be at the head of its queue. So it will dequeue X. Again, the token will flow this way, the token will flow this way, and this way. So the advantage of any algorithm that has a queue is basically starvation freedom, where we say that, look, you will have a queue, and ultimately you will come to the beginning of each queue. And when you come to the beginning of a queue, it is guaranteed that you will get it, right? So basically nobody can displace you from your position, and given the fact that the only direction in a queue that you can move is up, which means towards the head, ultimately it will come at the beginning of all queues, and you are bound to get the token, which in this case will happen. So given that we have seen this, token based algorithms are very simple. The key algorithm that you should focus on is the Mekava's algorithm. And this algorithm is kind of involved, but I think we have discussed this in great detail. The token based algorithms are quite simple.